So, back to the question. We have a ball or a hoop on an incline, and the question becomes, if I want to get the acceleration, what am I going to do? Free body diagram. So the trick here is we got to be smart about where we draw our the forces. So I clearly have a normal force. Wake up, normal force, right, coming perpendicular to the surface. What other forces are at work here?
Gravity.
Gravity. I'm going to draw gravity as coming from the center of the object. Are there any other forces acting on this thing? Yes.
Friction.
Friction. What direction does friction go?
Opposite of motion.
Opposite of motion. So that would be in what direction?
Up.
Up the incline. Okay.
What if we didn't though?
So in some ways, this makes some sort of sense, because clearly we know that at the bottom, it's not going as fast as it would be if it just slid down the incline, right? So clearly there has to be some sort of force opposing the mg sine theta acceleration. So now that I have my forces, I can write two equations. I can write sum of the forces parallel to the incline, mg sine theta minus force of friction. And that will equal ma. I also, though, need how am I going to determine what the friction is? So, is this kinetic or static friction? Static friction, right? So, we know that static friction is less than or equal to mu static times the normal force, right? So I can't just say mu static mg cosine theta here, right? So I need another equation. So this mass has translational acceleration, but it also has angular acceleration. So I can certainly write I alpha is r cross f. And the f in this equation is going to be force of friction. Does that make sense? So I can write force of friction is I alpha over r. Or remember that alpha is a over r. I can write this as IA over r squared. So now I can come back to this equation right here and rewrite this as MA is mg sine theta minus IA over r squared, or m plus I over r squared times A is mg sine theta, or my acceleration is the forces acting on the system minus the mass and rotational inertia term. And if I go back and compare this to what I got in the previous problem, remember we came up with an expression that looked like V is equal to root GH, and the idea was that that was the energy of a, in this case we used a hoop going down an incline. We can write that, I'm going to go back and write that as V squared is GH, and in this case we could say V squared is equal to G, and the H term just looks like a d sine theta. So H is equal to d sine theta. Is that clear? Are we good on that idea? Going back to where I was, let's plug in for, let's assume it's a hoop. So let's see, hoop, I of a hoop is mr squared. That's going to give me A is mg sine theta over m plus mr squared over r squared. That looks like mg sine theta over 2m. Perfect. The m's are going to cancel out, and I'm left with acceleration is g sine theta over 2. And if I go back to my v squared equation, I would get v squared is v0 squared 2a delta d. Delta d is just h sine theta. Sorry, I messed that up. Delta d is the length of that incline. Acceleration is this term right here, and the velocity initial was 0, so we're left with v squared is equal to g sine theta times 2 over 2 times delta d. The 2's cancel out, and I get exactly the same thing I had before. V squared is g sine theta d. V is equal to g d sine theta. So that's a way to look at, another way to look at rolling without slipping. So let's go back to, I guess, this equation here, which is a nice general equation for the acceleration down an incline. Assuming that we have kind of rolling without slipping. So on the previous screen, or previous slide, we came up with this relationship that the acceleration is mg sine theta over m plus I over r squared. You notice that dimensionally this works out. We've got mass on top, and then I over r squared is mass. We have mass on the bottom. Going back and remembering, we had a force of friction up the incline. We had a normal force, and then gravity pointed down, and we drew in an mg sine theta force going down the incline. And so what we'd like to do is go back and look at what that minimum friction is in order for it to roll as opposed to slipping. So the force of friction is given by mu Fn, which looks like mu mg cosine theta. And the other piece going back, remember we said that I alpha is equal to R cross F, which gave us that alpha is equal to R force of friction divided by I, angular acceleration is A over R. And so I can take this acceleration here, plug it in, and we can come up with a value for the force of friction. So I'm going to rewrite this slightly as R squared force of friction divided by I is equal to A, which is equal to mg sine theta over m plus I over R squared. I can solve for force of friction is equal to I mg sine theta over R squared times m plus I over R squared. And then with a little bit of effort, I can write this as follows. I can take and say that mg sine theta over, and I'm going to bring this in here and say m R squared over I plus 1, because I have an R squared here, I have an I here, is equal to force of friction, which is mu mg cosine theta. Force of friction is mu mg cosine theta. So with a little bit up ahead already. So with a little bit of effort, this mg and that mg will cancel out, and I'm left with tangent theta over 1 plus m R squared over I is equal to mu. And if you stop and plug in some values that we're familiar with, if I say that I of a disk, I of a hoop is mr squared, plugging that a number into here, I get mu is equal to 1/2 tangent theta. And remember that for a block on an incline, we said that mu static or mu static has to be greater than or equal to tangent greater than or equal to tangent of theta. So in order for it to roll, it turns out with using a hoop, it turns out that you can have basically half of the static friction and it will still roll, as opposed to this where I have a block on an incline. This result here, although I don't like to memorize results, this result here applies for all items. So for example, if I were to do a ball on ramp, I could rewrite this as tangent theta over 1 plus mr squared over a ball is 2/5 mr squared is equal to this minimum mu. So I should go 1 plus. Clean that up. 1 plus. So this would look like tangent theta over 1 plus 5/2, which would look like 7/10 tangent theta is equal to mu. Thank you very much.